As we embark on our AI journey, let us now delve into the 1960s, a decade marked by significant advancements in the field. 1960 ADALINE. ADALINE, which stands for Adaptive Linear Neuron, is an influential neural network model that was developed in 1960 by Bernard Widrow and Markey and Horff at Stanford University. ADALINE represents an important milestone in the early development of artificial neural networks and machine learning algorithms. It introduced the concept of adaptive learning, paving the way for more advanced models and algorithms in the field. The ADALINE model is a single-layer neural network that operates as a linear classifier. It consists of an input layer, a linear combination unit, an activation function, and an output unit. The input layer receives input features, which are multiplied by adjustable weights and summed up in the linear combination unit. The resulting weighted sum is then passed through an activation function to produce the network's output. The key innovation of ADALINE lies in its learning algorithm, known as the Widrow-Horff rule or the delta rule. The learning algorithm allows ADALINE to adjust its weights iteratively based on the difference between the network's output and the desired target output. The weights are updated in a way that minimizes the error between the actual output and the target output, using gradient descent optimization. The learning rule of ADALINE can be summarized as follows: for each input sample, the output is computed based on the current weights. The error, which is the difference between the computed output and the desired target output, is then used to update the weights. The weight update is proportional to the input value and the error, and it is performed in the direction that reduces the error. This iterative weight adjustment process continues until the network's performance reaches a satisfactory level. One of the notable features of ADALINE is its linear activation function. The linear activation function provides a continuous output that is directly proportional to the weighted sum of the inputs. This linear behavior allows ADALINE to model linear relationships between inputs and outputs. However, it also limits its capabilities in capturing nonlinear patterns in the data. ADALINE was initially developed for pattern recognition and pattern classification tasks. It demonstrated promising results in various applications, including speech recognition, image processing, and adaptive filtering. The model's ability to adapt its weights based on training examples made it suitable for dealing with noisy or dynamically changing environments. ADALINE's impact on the field of machine learning and neural networks was significant. It laid the foundation for subsequent advancements in adaptive learning algorithms and neural network architectures. The model's simplicity and effectiveness in linear pattern classification tasks inspired further research in the development of more complex neural networks capable of handling nonlinear problems. The development of ADALINE also led to the introduction of the concept of backpropagation, which is a widely used learning algorithm in modern neural networks. Backpropagation, first introduced by Paul Werbos in the early 1970s, is an extension of the ADALINE learning rule that allows for the training of multi-layer neural networks. ADALINE's success and its impact on the field can be attributed to its ability to learn from examples and adapt its weights to improve performance. This adaptive learning mechanism became a fundamental concept in machine learning and artificial neural networks. It opened up new avenues for developing more advanced algorithms that could learn from data and automatically adjust their internal parameters to optimize performance. In conclusion, ADALINE, developed in 1960 by Bernard Widrow and Markey and Horff, is a significant contribution to the field of artificial neural networks and machine learning. Its adaptive learning algorithm and linear activation function marked important milestones in the development of neural network models. ADALINE's success and influence paved the way for future advancements in the field, inspiring the development of more sophisticated neural network architectures and learning algorithms. Today, ADALINE's principles continue to underpin many machine learning algorithms, serving as the foundation for modern neural network models used in a wide range of applications. (1961) SAINT, Symbolic Automatic Integrator, was a pioneering expert system developed by James Slagle in 1961. It represented a significant milestone in the field of artificial intelligence, specifically in the domain of calculus problem solving. The primary objective of SAINT was to automate the process of solving calculus problems, focusing particularly on symbolic integration. Instead of relying on numerical approximation methods, SAINT aimed to derive exact solutions using symbolic manipulation techniques. SAINT approached problem solving by representing mathematical expressions as symbolic objects. These symbolic objects could be variables, constants, functions, or operations. SAINT employed a collection of rules and algorithms to manipulate these symbols and perform symbolic integration. One of the notable features of SAINT was its ability to generate step-by-step solutions that were human-readable and understandable. This made SAINT a valuable tool for educational purposes, as it could provide detailed explanations of the intermediate steps involved in solving calculus problems. The functioning of SAINT relied on a vast repository of rules and heuristics that encoded mathematical knowledge and strategies employed by humans in calculus problem solving. These rules covered a wide range of integration techniques, including substitution, integration by parts, trigonometric identities, and more. By applying these rules in a systematic manner, SAINT aimed to mimic human-like problem-solving strategies. When faced with an integration problem, SAINT first analyzed the problem and determined the appropriate integration technique to be applied. It then followed a sequence of rule-based steps to manipulate the symbolic expressions, simplify them, and obtain the final solution. While SAINT demonstrated promising capabilities in solving calculus problems, it also had its limitations. The system primarily focused on integration and did not address other aspects of calculus, such as differentiation or differential equations. Additionally, SAINT had constraints in handling more complex or unusual integration cases that required advanced mathematical reasoning beyond the scope of its rule base. Nevertheless, SAINT's significance lies in its pioneering role in the development of expert systems and symbolic manipulation techniques. It showcased the potential of artificial intelligence systems to automate complex problem-solving tasks and generate explanations that closely resembled human problem-solving methods. SAINT's impact extended beyond the domain of calculus. It laid the groundwork for subsequent advancements in symbolic computation, expert systems, and the broader field of artificial intelligence. The ideas and techniques introduced by SAINT served as building blocks for future expert systems that could tackle a wide range of domains, providing solutions and explanations for complex problems. Moreover, SAINT's influence can be seen in the development of modern computer algebra systems, CAS. CAS, such as Mathematica, Maple, and SIMPy, are widely used today for symbolic computation tasks, including calculus problem solving. These systems have built upon the foundations established by SAINT and have evolved to handle a broad range of mathematical domains and complex problem scenarios. In conclusion, SAINT, developed by James Slagle in 1961, was a groundbreaking expert system that focused on symbolic integration in the domain of calculus. It showcased the potential of AI systems to automate complex problem-solving tasks using symbolic manipulation techniques. SAINT's ability to generate human-readable step-by-step solutions made it a valuable educational tool. The ideas and techniques introduced by SAINT laid the foundation for subsequent advancements in expert systems, symbolic computation, and the broader field of artificial intelligence. SAINT's influence can still be observed today in modern computer algebra systems, and the ongoing pursuit of automating complex problem-solving tasks. 1963 Hierarchical clustering. Hierarchical clustering is a popular unsupervised machine learning technique used to uncover underlying structures and patterns in data. Developed independently by several researchers, including Robert L. Wilder and Joseph B. Kruskal in 1963, and Maurice S. Johnson in 1967, hierarchical clustering offers a flexible and intuitive approach to clustering analysis. We will provide a comprehensive summary of hierarchical clustering, its key concepts, algorithms, and notable contributions by authors in its development. 1. The concept of hierarchical clustering. Hierarchical clustering aims to organize data objects into a hierarchy of clusters based on their similarity or dissimilarity. Unlike other clustering techniques, hierarchical clustering creates a tree-like structure, known as a dendrogram, that displays the nested relationships between clusters at different levels of granularity. 2. Agglomerative and divisive hierarchical clustering. There are two main approaches to hierarchical clustering, agglomerative and divisive. Agglomerative clustering starts by considering each data point as an individual cluster, and then iteratively merges the most similar clusters until a single cluster is formed. Divisive clustering, on the other hand, begins with all data points in a single cluster, and recursively splits the cluster into smaller clusters until each data point is in its own cluster. 3. Distance metrics. To measure the similarity or dissimilarity between data points, various distance metrics are used in hierarchical clustering. Commonly employed metrics include Euclidean distance, Manhattan distance, and cosine similarity. The choice of distance metric depends on the nature of the data and the problem at hand. 4. Linkage criteria. Linkage criteria define the distance between clusters and play a crucial role in determining the order of merging, or splitting clusters in hierarchical clustering. Different linkage criteria include single linkage, complete linkage, average linkage, and Ward's method. Single linkage considers the minimum distance between two clusters, complete linkage uses the maximum distance. Average linkage calculates the average distance, and Ward's method minimizes the increase in total within cluster variance after merging clusters. 5. Algorithms for hierarchical clustering. Hierarchical clustering can be performed using different algorithms. Notable algorithms include the single linkage algorithm developed by Robert L. Wilder and Joseph B. Kruskal in 1963, the complete linkage algorithm proposed by Maurice S. Johnson in 1967, and the Ward's method introduced by Joe H. Ward Jr. in 1963. These algorithms employ different strategies for calculating distances and merging or splitting clusters. 6. Dendrograms. A dendrogram is a visual representation of the hierarchy of clusters created by hierarchical clustering. It displays the merging or splitting of clusters at different levels, revealing the relationships between data points and clusters. Dendrograms provide insights into the structure and similarity patterns in the data. 7. Notable contributions. Hierarchical clustering has seen notable contributions from various authors over the years. Robert L. Wilder and Joseph B. Kruskal introduced the single linkage algorithm in their paper, Finding Clusters in 1, 2, or 3 Dimensions, published in 1963. Maurice S. Johnson proposed the complete linkage algorithm in his paper, Hierarchical Clustering Schemes, published in 1967. Joe H. Ward Jr. introduced Ward's method in his paper, Hierarchical Grouping to Optimize an Objective Function, published in 1963. These contributions significantly shaped the field of hierarchical clustering and its applications. 8. Applications of hierarchical clustering. Hierarchical clustering finds applications in various domains. It is used in biology to analyze genetic data and classify species based on their similarity. In marketing, it helps segment customers based on their purchasing behavior. It is also applied in document clustering, image analysis, social network analysis, and anomaly detection, among other fields. The flexibility and interpretability of hierarchical clustering make it a valuable tool for exploratory data analysis and pattern discovery. Hierarchical clustering, developed independently by researchers like Robert L. Wilder, Joseph B. Kruskal, Maurice S. Johnson, and Joe H. Ward Jr. in the 1960s, offers a powerful approach to uncovering underlying structures in data. With its agglomerative and divisive strategies, distance metrics, linkage criteria, and dendrograms, hierarchical clustering provides a versatile and intuitive method for clustering analysis. The contributions of these authors have significantly advanced the field and laid the foundation for its applications in various domains. Hierarchical clustering continues to be a valuable technique for data exploration, pattern recognition, and data-driven decision-making across industries. 1966 ELIZA. ELIZA, developed by Joseph Weizenbaum, was a groundbreaking natural language processing program that simulated conversation by utilizing pattern matching techniques. It represented a significant milestone in the field of artificial intelligence, and had a profound impact on the development of chatbots and human-computer interaction. ELIZA was designed to emulate a Rogerian psychotherapist, named after Eliza Doolittle from George Bernard Shaw's play, Pygmalion. The program aimed to engage users in conversation and provide them with a therapeutic experience by analyzing their inputs and generating appropriate responses. The key feature of ELIZA was its ability to understand and respond to natural language inputs using pattern matching. It employed a set of predefined patterns and rules to identify keywords and phrases in user inputs and generate corresponding responses. These patterns acted as templates for transforming user inputs into appropriate questions or statements. ELIZA used a technique known as rephrasing to transform user statements into questions that encouraged further elaboration. By reflecting user inputs back to them as questions, ELIZA simulated a conversation where the user played both the patient and the therapist. This technique aimed to stimulate self-reflection and provide a sense of understanding and empathy. For example, if a user input contained phrases such as, "I feel sad," ELIZA might respond with a question like, "Why do you feel sad?" By identifying keywords like "I" and "feel" and using pattern matching techniques, ELIZA could generate appropriate responses that seemed engaged in a conversation. ELIZA's simplicity and effectiveness relied on its ability to recognize and respond to key phrases without truly understanding the underlying meaning. It demonstrated that by using clever pattern matching techniques and well-crafted responses, a program could create the illusion of understanding and communication. The program gained significant attention and popularity, as users found the experience of interacting with ELIZA to be surprisingly engaging. Many users were convinced that ELIZA possessed human-like qualities, even though it operated solely based on pattern matching and rule-based transformations. ELIZA's impact extended far beyond its initial purpose as a psychotherapist simulation. It influenced the development of chatbots, natural language processing, and human-computer interaction. The program inspired researchers to explore new ways of simulating conversation and understanding human language, leading to advancements in machine learning and deep learning techniques applied to natural language processing. One notable legacy of ELIZA is the Turing test, a benchmark for evaluating a machine's ability to exhibit intelligent behavior indistinguishable from that of a human. ELIZA's conversational capabilities, and its ability to fool users into thinking they were interacting with a human, led to debates and discussions about the nature of artificial intelligence and the limits of machine understanding. Joseph Weizenbaum, the creator of ELIZA, himself expressed concerns about the program's influence. He argued that people's willingness to confide in ELIZA and attribute human-like qualities to it revealed the dangers of over-reliance on machines for emotional support and therapy. In conclusion, ELIZA, developed by Joseph Weizenbaum in 1966, was a pioneering natural language processing program that simulated conversation using pattern matching techniques. It emulated a Rogerian psychotherapist, engaging users in conversation and providing therapeutic experiences through its clever use of rephrasing and pattern-based responses. ELIZA's influence extended beyond its original purpose, inspiring advancements in chatbots, natural language processing, and human-computer interaction. It prompted discussions about the limits of machine understanding and the nature of artificial intelligence, leaving a lasting impact on the field. 1969 The XOR Problem. Perceptrons is a 1969 book by Marvin Minsky and Seymour Papert that analyzes the capabilities of perceptrons, a type of artificial neural network. The book was influential in the field of artificial intelligence, and it is credited with helping to slow down the development of neural networks in the 1970s. The book is divided into 3 parts. The first part introduces the perceptron and discusses its mathematical properties. Minsky and Papert introduce the basic concepts of perceptrons and lay the groundwork for understanding their limitations. They start by defining the perceptron as a mathematical model of an artificial neuron. They discuss the structure of perceptrons, which consists of input nodes, weighted connections, an activation function, and an output node. The authors explain how perceptrons can learn by adjusting the connection weights based on input patterns. The authors then delve into the concept of linear separability. They illustrate how perceptrons excel at solving problems that are linearly separable, where a single straight line can separate the input patterns into different categories. They provide mathematical proofs and examples to support this notion. This part aims to provide readers with a solid understanding of the capabilities and limitations of perceptrons. The second part surveys the work that had been done on perceptrons up to the time of the book's publication. Minsky and Papert examine how perceptrons can learn and classify simple patterns, such as lines and circles. They provide detailed explanations and mathematical analyses for each case, exploring the boundaries of perceptron capabilities in solving pattern recognition problems. Importantly, this part also delves into the XOR problem, a key highlight of the book. The authors demonstrate that perceptrons, with their linear activation functions, fail to learn and classify the XOR problem correctly. They mathematically prove that the XOR problem is not linearly separable, and explain why single-layer perceptrons cannot handle such non-linearly separable problems. The third part discusses the limitations of perceptrons and the challenges that need to be addressed in order to build more powerful neural networks. This part delves into the realm of complex patterns and the limitations of perceptrons in handling them. Minsky and Papert introduce the concept of multi-layer perceptrons with hidden layers as a solution to overcome the limitations of single-layer perceptrons. They mathematically prove that multi-layer perceptrons, with their ability to create non-linear decision boundaries through hidden layers, can handle non-linearly separable problems. One of the main contributions of perceptrons is the proof that a single-layer perceptron cannot solve the XOR problem. The XOR problem is a simple logic problem that cannot be solved by a linear function, and a single-layer perceptron is a linear function. This proof showed that perceptrons are limited in their capabilities, and it led to a period of time known as the AI winter, in which funding for AI research was cut significantly. However, perceptrons also made some important contributions to the field of neural networks. The book introduced the concept of the multi-layer perceptron, which is a neural network with multiple layers of neurons. Multi-layer perceptrons can solve problems that cannot be solved by single-layer perceptrons, and they are the basis for many modern neural network architectures. The key points of the book are: 1. Perceptrons are simple neural networks that can only learn linear functions. 2. The XOR problem is a simple logic problem that cannot be solved by a single-layer perceptron. 3. Multi-layer perceptrons can solve problems that cannot be solved by single-layer perceptrons. The development of neural networks is limited by the difficulty of training neural networks to learn complex functions. A multi-layer perceptron is a type of neural network that consists of multiple layers of interconnected neurons. These hidden layers allow the network to learn nonlinear functions, which is a crucial feature for solving complex problems. Unlike linear functions, nonlinear functions cannot be represented by a single-layer perceptron. This is where the multi-layer perceptron comes in handy. The most famous example of a problem that cannot be solved by a single-layer perceptron is the XOR problem, as aforementioned. However, a multi-layer perceptron can easily solve this problem by learning the nonlinear function that represents it. Interestingly, the book Perceptrons did not provide a detailed description of how to train multi-layer perceptrons. Instead, it discussed the challenges of training them. One of the main challenges is that the training process can be very slow. Another challenge is that the training process can be very sensitive to the initial weights of the neurons. Despite these challenges, multi-layer perceptrons have become a powerful tool for solving a wide variety of problems. They are used in applications such as image recognition, natural language processing, and speech recognition. The book Perceptrons was a controversial book when it was published, and it is still debated today. However, there is no doubt that the book had a significant impact on the field of artificial intelligence. It helped to define the limits of what perceptrons can do, and it inspired researchers to develop more powerful neural network architectures. 1969 Shakey. Shakey, developed by the Stanford Research Institute, SRI, was a pioneering mobile robot that demonstrated significant advancements in the field of artificial intelligence. It represented a major breakthrough in robotic capabilities, showcasing the potential of AI techniques in enabling autonomous navigation and interaction with the environment. Shakey was designed to operate in real-world environments, making it distinct from stationary or limited mobility robots of the time. The robot stood about 6 feet tall and was equipped with a variety of sensors and computational systems that allowed it to perceive and reason about its surroundings. One of Shakey's notable features was its ability to navigate autonomously. The robot employed a combination of sensors, including television cameras and rangefinders, to perceive its environment. These sensors provided visual and depth information, enabling Shakey to generate a representation of the world around it. To navigate through its environment, Shakey utilized a path planning algorithm called the A*search algorithm. This algorithm allowed the robot to plan optimal paths from its current location to a specified goal location. Shakey's ability to reason about its environment and compute these paths in real time demonstrated its advanced intelligence and problem-solving capabilities. Additionally, Shakey showcased the integration of perception and action. The robot had the capability to manipulate objects in its environment, demonstrating basic physical interaction skills. This was achieved through the use of an arm and gripper mechanism, which allowed Shakey to grasp and move objects in its surroundings. The decision-making processes of Shakey were guided by logical reasoning and rule-based systems. The robot employed an AI technique known as STRIPS, Stanford Research Institute Problem Solver, which utilized symbolic representation and deduction to reason about its actions and goals. Shakey could formulate plans, execute them, and adapt its behavior based on the changing environment. However, it is important to note that Shakey's movements were relatively slow and deliberate. The robot had to carefully analyze its environment and plan its actions, which limited its speed and agility. Nevertheless, Shakey's ability to operate autonomously in complex environments represented a significant leap forward in robotics and AI. The development of Shakey had a profound impact on the field of robotics and AI. It served as a platform for research and experimentation, inspiring subsequent work in areas such as computer vision, path planning, and knowledge representation. The successful development of Shakey also paved the way for advancements in mobile robotics and autonomous systems. The integration of perception, reasoning, and action in Shakey's design laid the foundation for future robots that could navigate and interact with the real world in more sophisticated ways. Furthermore, Shakey influenced the development of AI technologies beyond robotics. Its use of logical reasoning and rule-based systems demonstrated the power of symbolic representation and deduction in problem solving. These concepts became foundational in the field of knowledge-based systems and expert systems, which aim to replicate human expertise in specific domains. The impact of Shakey extended beyond academia and research labs. The project generated significant public attention and interest, capturing the imagination of people worldwide. Shakey became an iconic symbol of the potential of AI and robotics, demonstrating the possibilities of intelligent machines in everyday life. In conclusion, Shakey, developed by the Stanford Research Institute in 1969, was a groundbreaking mobile robot that showcased the capabilities of artificial intelligence in autonomous navigation and interaction with the environment. It utilized sensors, path planning algorithms, logical reasoning, and rule-based systems to perceive, reason, and act in complex real-world scenarios. Shakey's contributions had a profound impact on the field of robotics, inspiring further research and advancements in AI technologies. It represented a significant step forward in the development of intelligent machines, and continues to be recognized as a landmark achievement in the history of robotics and AI.